Okay, this is where we are. So we're solving linear systems. We know what that means to solve a linear system, don't we?
Yes.
What does the solution to a linear system represent? What does that mean, Dad? It's an ordered pair. That means what?
Where the lines meet.
Where the lines meet. Where they cross each other, right? Where they intersect. The solution to a linear system, ordered pair where they meet. And graphing is definitely, it's a fine method. What are some of the good things about using the graphing method? What's good about it, Ryan?
It's like quick, it's almost hard to make mistakes.
Quick and easy and hard to make a mistake. Who agrees with that?
We
Really? Oh, what if your equation is 1/2 x plus 0.7 y equals 967?
Yep, with whole numbers.
easy.
It's easy with whole numbers and small ones. And where the solution is what? Is a nice integer x and an integer y. Maybe then. And it has to be easy if you love graphing. I never heard of it. So maybe for some people that's not great. But yes, they can be. First of all, and what about what the solution is? Like right in your face. I don't know. It's a very graphic way. You know exactly what you're doing. What's bad about it? What's bad about it? Yeah.
If you get like a half or something, you can do different numbers.
Yeah, like it's very hard. If your solution aren't nice integer numbers, you very hard to tell from looking at a graph what the values are. You can do your best to guess, but you may not get there. So then we looked at substitution method. So who can describe the substitution method? Claire, what do you think it is? How do you describe that?
You so if it has like if it has like an x, so say it says x equals 2 and then the next one is y equals x plus 5.
Okay.
So you plug in the x to get something.
Right. All right. Because the problem with our two equations is that they're two variables. We don't know how to solve it. So what you do is you solve one of them for either x or y, and then you substitute that into the next equation. You get a big long equation, but there's only one variable, and you solve it. Once you find that, you plug back into the other variable, and so on. So then we started with elimination. Elimination is when you add the two equations together, and you can eliminate, or one of the variables drops out. And so you find one, then you plug in to find the other. And so sometimes it's easy if you have sames or opposites for your x's or y's, and sometimes you have to multiply through, right? So you do that. You choose a variable and you find the least common multiple, multiply one or both equations by that constant, right? So that you will get sames or opposite coefficients, so that you can add or subtract to get rid of it. Once you get one variable, you plug in to find the other variable, and you solve put the equation, or put that ordered pair in both equations. So that's where we've been. So we have some special types of linear systems. Now there's going to be a lot of mathy words here, so you don't necessarily have to know them for a test, but if you're reading textbooks or in the future, you may see some of these words. So I want you to kind of be exposed to them a little bit. So here's the first type. Let's see how this works. So if a system of equations is consistent and independent, that means what? It means that there is a solution. So you'll have two intersecting lines. It's consistent, meaning there is a solution, and independent, we can find it. Let's see. The slopes of the two lines of the equations will be different, and the solutions, you have one solution. So that's one like this. There is one solution. This line and this line will have different slopes. So for consistent dependent, these will have solutions too, but it's a little bit different. You get one line. So here's one equation, and here's the other equation, right on top of it. So they have the same slope and the same y-intercept. There are infinitely many solutions, because remember, solutions are the xy pairs on the line. So all the solutions will be on that line. The last kind is called inconsistent. It means there is no solution. And those when you have parallel lines. So they have the same slope with different y-intercepts, and there is no solution, because if your solution is where the lines meet, right, here's one, here's an infinite number, they never meet, so you don't have any. So here's an example of what that looks like. So here's example one on your paper. Everybody's looking?
Yeah.
Yep. Okay, you with me? Who's with me? Raise your hand.
I'm with you.
Yay. Okay, good. So 3x plus 2y equals 10, and 3x plus 2y equals 2. So if I want to do this by graphing, With Ryan, you told me it's the easy method. So how do I do this by graphing?
You get the x plus 1
Okay, so let's see, if I start with 3x plus 2y equals 10, right? Subtract that 3x, negative 3x plus 10, divide by 2, right? So negative 3 halves x plus 5? So how does that work again? So n is negative 3 halves, and b is 5. So let's see, 1, 2, 3, 4, 5. This says what? Go down 3, right 2? 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. There's the first one. Now I gotta do this again. So this is the easy method, right? This is like a lot of work. So let's see. 3x plus 2y equals 2. So 2y equals negative 3x plus 2. Subtracting the 3x. Divide everything by 2. Plus 2 over 2 is 1. I go to 1. Same thing. Down 3, right 2. 1, 2, 3. What happened? What? Yeah. 1, 2, 3, 1. So the graphing method, what are the solutions? No solutions. Lines are parallel. Same slope, different y-intercepts, right? Parallel lines, no solutions. They don't ever intersect. Now let's say we solve this using the elimination method. So with the elimination method, we're looking for sames and opposites, or opposites. So let's see. Oh, lots of sames. So let's make one opposite. So maybe multiply through by a negative. The top one stays the same. And the bottom one, everything flips, right? If it's positive, it goes negative. If it's negative, it goes positive. Okay, so let's see. I add. Oh, look what's happening. That's 0. And so is that. Everything's 0. And I get 10 minus 2 is 8. Really? 0 equals 8? What? So what's happening? No solution. When you get, look, the x's and the y's are gone, and you're left with nonsense. This is a false statement, right? That can't happen. No solution. So if you solve it graphically, you will see parallel lines. And if you solve it algebraically, you'll see nonsense like this. So when you eliminate and you're left with a false statement, there are blank solutions to the linear system. No solutions. Okay? And so either method will show the same thing there. No solutions. Okay? So let's try another one now. Oh, it's got a fraction in it. Oh, no. Well, first of all, let's use the graphing method. I'm okay with this for graphing, right? This one I got to fix a little bit. X minus 2y equals negative 4. So negative 2y equals negative x minus 2. What did I just do there?
You added
I subtracted x from both sides. So hopefully we're getting a little tiny bit faster with that. Now what am I doing? Everything gets divided by negative 2.
X minus 2y equals minus 1.
What?
Equals minus 2.
Oh, I should do. That's a 4, that's a 4, that's a 2. So here's my equation. That's this one. So I can graph that. That's 2. Up 1, right 2. Up 1, right 2. Down 1, left 2. Okay. So that's the first one, right? Now I can go and do this one. It's y equals half x plus 2. Look at this. If I graph that, I'm just going right on top. So what's going on here? Where do the lines intersect?
Everywhere.
So how many solutions?
Infinite.
There are infinitely many solutions, and all those solutions live on the line y equals half x plus 2. So it's not all real numbers. Some people make a mistake and they just say, all real numbers. Well, no, because how about this real number? 1, negative 2. Is that a solution? No. Only the solutions that are on the line. Only those xy pairs on the line. Now, if you were to solve this by elimination, sure, we can do that. So the first thing I'm noticing here is that they're not in the same format. So I think, you have choices. I'm going to move this over. So it becomes negative half x plus y equals 2. I also do not like having fraction.
Yeah, I was just talking about that.
Yeah, you were talking work, that's okay. So, I've moved this over. How do I get rid of that 2 again? Because it's annoying having a fraction.
Multiply by 2.
Multiply what by 2?
Everything.
Everything. So this becomes what? Knocks that one out. You get negative x plus 2y equals 4. And now I'm rewriting the one on top. Right? This one. That goes here. So now I'm going to add. Oh, look, what happens? 0, 0. Well, that's a true statement. Doesn't 0 equal 0? Yeah, sure it does. But no variables, right? Everything's kind of wacky. So when you are solving something with the elimination method, you get a true statement. What is it trying to tell you? How many solutions are there?
Infinitely many.
There are infinitely many. I think I know what there's infinitely many solutions, but remember, they're not all real numbers. The solutions are the xy pairs on the lines themselves. So like a solution might be 0, 2. Another solution might be 2, 3. But there are an infinite number of points on that line. That's why there's infinitely many solutions. Question?
The graphing one is easier than the animation.
Well, maybe. What if these weren't such nice little easy things to graph? Then it might not be. But you don't always know ahead of time what you're going to do. I dare say most of the time you're going to use algebraic methods to solve this. Yeah. So that's what it looks like. Okay. So identifying number of solutions. There's a question. Okay, come on, I'm moving on to the back now. So identifying how many solutions. Remember, there could be one, there could be none, or there could be infinitely many solutions. So one way to do it is to just try and solve the equation and see what happens. If you want to know ahead of time, here's a way to do it. You write both equations in slope-intercept form, and then you compare the slopes and the y-intercepts. If the slopes are different, what does that tell you? How many solutions, if any? Yeah? 1. Because that means like one has a slope like this, one has a slope like that. They're different. Eventually you're going to meet somewhere. So if the slopes are different, you have a solution. Now if the slopes are the same and your y-intercepts are the same, then what? What can you say about the solutions? What? Slopes are the same. So let's just, slopes are the same and y-intercepts the same. When that happens, you have the same line. There are infinitely many solutions, and those solutions live along this line. The xy pairs on that line. Now, if the slopes are the same and the y-intercepts are different, then what? Because this means parallel lines. And they will never meet. So there's no solution to that linear system. So if you want to know ahead of time, you can do that kind of analysis. So for example, if I just want to know how many solutions, how many? Okay, so let's see. Well, 5x plus y, but when slope of the equation 1, well, how am I going to find the slope of this thing? What do I have to do here first?
Into y equals.
So how do I do that, Cole?
You have to, first you're going to minus 5x on the top one. Subtract 5x.
Subtract 5x. So what's my slope here?
Your slope is 2. Yeah.
Why don't then I supposed to be? Yeah. So m is slope, b is y-intercept. So what's my slope?
Negative 5.
And what's my y-intercept?
Negative 10.
Okay. And I'm going to repeat that process for this guy. Negative 10x minus 2y equals 4. So how do I get this into slope-intercept form, Matthew? Okay, so we're going to add that 10x. Then what? Divide everything by negative 2. So y equals negative 5x minus 2. So what's the slope of this guy? And what's the y-intercept? Slopes are the same, y-intercept's the same. What can we conclude about this system?
They're infinite.
Infinitely many. These are the same equation, aren't they? I feel like you don't know when to say infinitely many or none. So look at that. Y equals negative 5x minus 2. Y equals negative 5x minus 2. Same line. Where do they intersect? Everywhere.
Every time.
right? So now let's look at one like this one. 6x plus 2y. So we have to do the same thing now. Solve for y. Oh. Okay, so subtract that 6x. Who's having an easier time putting these into y equals mx plus b form? This used to be a really, really hard thing to do. Are you feeling a little bit better solving for y now? If you're not, definitely go to an algebra clinic, work on this. There is no algebra clinic today, but when there is one Wednesday, one Thursday, right? Divide everything by 2. So I'm getting y equals negative 3x plus 3x. Okay. What's my slope? Negative 3. And y-intercept is 3 halves. Okay. I'm glad I don't have to graph this, right, Ryan? This one's not as easy to graph. So let's see what's going on with this one. This is the second equation in the system. So again, subtract that 6x and divide everything by 2. So that becomes, negative 3x minus 5 halves. So let's see, slope is negative 3, and this is negative 5 halves. Okay, so slopes are the same, y-intercepts are different. So what do I say about those two lines? Yeah, they're parallel lines, so there's not going to be any solutions. And if you look up here, look at that. Same, different. If you see same, different, these are going to be parallel lines. This one, you can almost see it. If I multiply this through by 2, I get 10x plus 2y equals negative 4. And if I multiply that again by a negative number, negative 1, I get negative 10x minus 2y equals 4. Compare that with this. Same thing. So sometimes you can manipulate and see that they're the same. Yes?
You see something like that on a test? Can you just say equations are the same?
Yeah, now what you would do is you always want to show me why you're thinking what you're thinking. Say, you know what? I can multiply this top one by negative 2 and I get the exact same equation. Therefore, there are infinitely many solutions. Absolutely, you can do that. Yeah. Or you can say, look at this, because the x and y variables are the same, the only difference is in the numbers, you're going to come out with no solution. If you do this, you're strengthening your case though. So it's not bad to do that whole thing. So we get down to practice, really. That's kind of all there is to today's work. So what I want you to do is without solving the linear system, tell whether it has one solution, no solution, or infinitely many. And if it has one, find it. And I tell you what I'm going to do. For this first row, those are your directions. For this second row, just try and solve them. Because I want you, most of the time, you're really not going to do that analysis ahead of time. You're really not. You're just going to go dive in. So I want you to be kind of aware of what does it look like when you're solving and you get something funny. Okay, so the first one, I want you to find out ahead of time. One solution, no solution, infinitely many. Doing what you look for the y, you look for the mx plus b business, right? Compare slopes. This one, I just want you to go ahead and solve and draw your conclusions based on what's happening. All right, go ahead and try it. Okay, so you may not have finished, but let's see if we agree. I will when we get a little quiet. So shush. The top, you were supposed to solve for y. When I solve for y here, I got different slopes. I think this one has a slope of 1/3, right? 1/3 is the slope of this one, and 2/3 was the slope of that one. So they're different. So I knew I could just go ahead and solve it, and so I did. This was nice because I had some sames. So really, all I had to do here was basically flip signs, because that's multiplying through by a negative. So negative x equals 3. Means x is negative 3, right? Where that came from, plugged in, got my y, checked it. This one, the slope here, this one's kind of easy to see what this is. Y equals negative x minus 2. My slopes are the same, but my y-intercepts are different. These are parallel lines. There will be no solution. This one was maybe a little bit harder to see. But what did I get for this one? Y equals 3 halves x plus 3?
Y equals 3.
And the other one is y equals 3 halves x plus 3.
Yeah.
They're the same equation, the same line. Therefore, there were infinitely many solutions. All the solutions are on this line, the xy pair that make these true. Correct? Now, when you do these other ones, I said, don't even do that first, because you're not gonna do that. In practice, you're just gonna jump right in. You're gonna say, ooh, sames or opposites, I got a bunch of sames. Maybe if I multiply through by -1. So I'll rewrite the top one. And the bottom one, I'm just gonna flip signs, basically, right? And then I've got my opposites, but they're both opposites. So 0 equals -12, that's crazy. So when you get a false statement like that, it means there's no solution. So if you had solved this for y, you would see parallel right. This one, I think we were just able to multiply the top by 3, right? -6x plus 6y equals -48. That becomes -3x, that goes away. -18, x equals 6, plug it in, y equals -2, check them out. So this one solution. This one, like, uh-oh, right? So how would you get rid of this fraction? Yeah? What do you multiply by 4?
Everything.
Everything. Let's multiply by 4. What? You can, but you know, most of the time you're not gonna do that test ahead. I'm just gonna jump in and try and
That
solve
was
it.
in my head, so I just like did it that
Right,
way.
but usually if I give you a page of these to do, you're not gonna do that, because it's a big long extra step, isn't it?
Not really.
Well, but you don't have to.
Easier,
You
but-
don't have to, because
Yeah.
now, let's say, oh, I wanna make this look like that one. I'm gonna move the 3x over here. And so that's this one, right? So let me copy the top one down. And let's see what happens. Look, they're both opposites. That's 0, and so is that. Infinitely many solutions. So when you're solving these, you may come across these little oddballs. And so I just want to make sure you know what to do. So a quick summary here. Linear systems may have one solution. That's when you have different slopes and the lines will intersect. You may have infinitely many. That's when the two equations are really the same equation. They're one line on top of the other. Or you might have no solution. The two equations have the same slope but different y-intercepts. They don't intersect. So you can find the number of solutions if you want ahead of time by looking at slopes. Slopes are different, there's one. Same slope, same y-intercept, same line, infinitely many solutions, same slope, different y-intercepts, parallel line, no solution. And that's all she wrote.